Well, I did it again, so now we're on part two. My computer, I got to turn off the lights. My computer also died on me. I didn't have it plugged in. I apologize. So, yeah, the number you should have gotten was 40.917 as our estimate. You should see what's going on here with our estimate. We'll talk about that a little later. Now we're going to look at how to do right-hand Riemann sum, and it's the same idea, but now we're going to do it from the right side. So on this case, we're doing the interval 1 to 7 again, same function. We're going to subdivide the area into two lengths of 2. So now when I draw my first rectangle, I'm going from 1 to 7. So if my length is 2, I've got to start over here at 3. And I'm going to draw the rectangle so that now you can see the left vertex, this vertex, does not hit the curve. It's the right vertex that does. So now the height of rectangle 1 will not be f of 1 because f of 1 is too short. We need it to be taller, and f of 3 will represent the height of the first rectangle, okay? Then if I go to 5, that's going to be right-hand sum, so rectangle 2 will be right there, and the right-hand vertex is hitting the curve, and then our rectangle 3 is there. So again, because we're doing a right-hand sum, we're never going to use 1 to calculate a height. We are going to use the 7, though, because we got everything shifted to the right now. So our first height will not be f of 1 because it's a right-hand sum. So again, we're going to look at approximating the exact area, and I'm going to keep stressing that this definite integral from 1 to 7, which we'll figure out next lesson how to do that, that's the exact area. It can be approximated by doing our right-handed sum, which is going to be the width of each rectangle is 2, and we can factor that out, times the height of each rectangle, which is going to be f of 3 is actually the height of the first rectangle. Again, we don't use the 1, plus f of 5 plus f of 7. That's going to be an approximation from the right-hand sum. Notice that this right-hand sum has, we are doing the white area as not enough. It's missing this amount of area and this amount of area, and then the peach was the extra, right? That's not peach. Is that my peach? Okay. Is that the same color? Am I crazy? That is. All right. Then it's got too much area here. So in this case, our approximation, whatever we get, is going to be an under approximation. It looks like there's far much less area than there is extra area. So you're going to pause the video and work this out. You still have that same function. So let me see here. I have this one here. This should be 34.66 repeating, so we'll round it at 3 decimal places. That's our approximation using a right-handed sum here. All right, and let's do the next one. Now our intervals will be length 1 unit from 1 to 7. So again, I'm using the right-hand side to go up and draw till I hit the curve. For each interval, I start on the right, hit the curve, draw over, draw my rectangle. So when we find the area of all these rectangles, what are there, 6 of them, right? 1, 2, 3, 4, 5, 6. I'm missing some area on my approximation. We're missing all these spaces here. We've got a little bit of extra area over here and over here. So this looks like this will also be an under approximation. So this area, the definite integral, which represents the exact area, can be approximated by doing the area of these rectangles and summing them. So we know their width is going to be 1 for each rectangle, and the height of the first rectangle is now f of 2. And then f of 3 plus f of 4 plus all the way up to f of 7. So notice we never start with the 1 because we're doing right-handed, but we always end with the 7. You see that? We never start with the 1, but we always end with the 7 because it's a right-hand. All the rectangles have been shifted right is what you can think, or I don't know, that's how I think about it. All right, so you're going to calculate that area. We know it's going to be an under approximation. So again, you can pause the video. I'm getting 37.6 repeating. So there's our under approximation. Now let's do the right-hand sum with intervals length of 1/2. So again, I'll draw this out. Again, I'm going to go over half over to the right. There's my first rectangle. I'll draw this. You can pause it and draw it as well and see if you can calculate the approximation and get ahead of me if you like. And we'll come back and see what we have. All right, so this is the picture. You can see there's more missing white area than there is extra area in the peach part. We've got a lot of rectangles, so I'm not going to number them. So this will be an under approximation. I'll write out what you should have done if you have that done already. Whoops, not 4, 7. So the exact area is represented by the definite integral, can be approximated by the area of all these rectangles. These rectangles have width of 1/2. And then the height of the first one is f of 1.5. Plus the height of the second one is f of 2 plus f of 2.5. And so on. We continue the pattern. Notice we do not start with f of 1 because we're doing a right-handed sum. We throw out the leftmost endpoint. We don't use that to calculate our height. F of, what's the last one we do? 7, right? So I'll just say 6.5 plus f of 7. Because it's a right-hand sum, we end with the rightmost endpoint. And when you did all that out on your calculator, like I know you did, your approximation, which is an under approximation, is 38.917. All right, so what happens to the approximations as the length of the rectangles decrease? I'm talking about the width, really. As I make the interval smaller, we get more rectangles. What do you think happens with the approximations? And we'll just say that as the width, I know they use the word length, but I've been using width. So as the width of the rectangles decreases, the closer the approximation of the area gets to the actual area. The error starts reducing. If you look at this amount of error, those are pretty small colored in spots versus when I did the first one when I had wider rectangles. There's much more error going on there, right? So that's what I just talked about. So we'll say the smaller the width of the rectangles, the less error, or I'll call it overage / underage area there seems to be. The error gets less and less. All right, so on these approximations, we're going to try the something called the midpoint approximation. So switch that over. So here's how we're going to do a midpoint. On this one, you're going to use both endpoints, both the 1 and the 7 when you draw your rectangles. It might not show up in your heights, but we're going to use them when we draw the rectangles. So we're going from 1 to 7. We want lengths, or I should say widths, of 2 units. So when I draw my rectangle, it's going to start coming up here. But we don't hit either the left side or the right side that hits the curve, but it's actually the midpoint of the two. So it's the height of the midpoint. So the in between of those two sides of the 1 and the 3, the point right in the middle is 2. The x value in the middle is 2. So it's that height. That's going to determine the height of our rectangle. Instead of using the left corner of the rectangle or the right corner to hit the curve, it's the midpoint that hits the curve. And so the next interval is 3 and 5. So the middle of that is 4. So I'm going to use 4 as my next, the height of the 4 as my next height of my next rectangle. And then we're going from 5 to 7. It's got a width of 2. So 6 is the midpoint there. So we're going to use the height of the midpoint, which is 6. The height of the midpoint we're using. This green area could be an approximation for the curve. Okay, so I'm going to get rid of this part because we're going to talk about over and under approximations. So we've got, I can number these because there's only 3 of them. So how are we going to find this area? Well, the exact area is represented by the definite integral from 1 to 7. It's going to be approximated by the midpoint, the areas, the sum of the areas of these midpoint rectangles. So I know their width is 2. I'll factor out the 2 so I don't have to write it every time. And then the height of the first rectangle comes from the height of the midpoint of it. So it's really f of 2 plus the height of the second rectangle is f of 4 plus the height of the next rectangle is f of 6. You do that on your calculator, you should get an approximation of 40.66 repeating, so we'll round it to that. Let's see, we've got some overage area here. We've got some overage area here and some overage here. We've got some underage there, underage there, underage there. So is that an over or an under approximation? That one's a little tougher to tell because a lot of those areas look symmetric, but I'm going to say that it looks like to me to be an over approximation here. Let's move on to the next one. So now we're going to do widths of 1 unit. We're still doing the midpoint thing, right? So we're going from 1 to 7, but now they're 1 unit long. So each rectangle is like this. Oh, whoops, I just drew a left-handed one. So we want to go to the midpoint. So halfway between 1 and 2 is right there. That's going to be our height. So it's helpful to draw the height first, I think. Whoops. So there's our midpoint. There's the height. Now we can come down along 1 and along 2. Stupid light went off again. Now we're doing a rectangle of width 1, so it's 2 to 3. So the midpoint of that is 2.5. So the height of 2.5 is right about there. There's rectangle 2. Now I use 3.5. I go up to the curve. There's my height for 3.5. And then 4.5 is the midpoint between 4 and 5. And 5.5 looks like it's right about there-ish. And then for the last rectangle, we're using 6.5. All right, so this looks like it's got some overage area here, some overage here. And then it's got some underage, like this area here is not accounted for. All right, so I just paused it and colored the rest in. So you got some white, some underage area. And now you're going to calculate the approximation. So from 1 to 7, the exact area can be approximated by the area of the rectangles. They have a width 1, so you can factor that out. And it's going to be f of 1.5 because that's the midpoint between 1 and 2. And then f of 2.5 plus f of 3.5, so on and so forth, up to f of 6.5. And again, on your calculator, you can do that by just kind of plugging in your stuff, using that function notation, and you get about 40 0.16 repeating. So we'll call that our estimate. Now we're going to use the last kind of version here. We're going to use a trapezoidal approximation. We're going to use some trapezoids. So what's going to happen here is we're going to try to get even a better fit to the curve by using trapezoids. You do have to remember how to find the area of a trapezoid, which is this formula right here. Okay. B1 and B2 are the parallel sides, and H is the distance between those parallel sides, right? So if you have a trapezoid, if that's B1 and that's B2, it's because they're parallel, right? And then the height is that perpendicular distance. Now, the trapezoids we're going to be building are going to be right trapezoids, we'll call them. So where one of the sides is a right angle, which makes that the height. And then we've got our base 1 and our base 2, and they're going to be stood up kind of on their side, on their right perpendicular side. So we're going to be doing trapezoids like this, where B1 and B2 will be those sides, and the height of the trapezoid will be that guy. We just sort of turned it on its side. And those are the kind of trapezoids we're going to be using here. So they want us to do a trapezoidal Riemann sum with interval lengths, or what does it say? Some lengths of 2. So the heights here are going to be 2. So when I draw my first trapezoid, again, this is the base part, right? This is the height part, and it's on its side. It's the perpendicular part. So that's our height. These are the parallel bases, right? And what we're going to do is, to be a little more exact, we're going to stop that base there at the curve, and the other base is going to stop at the curve. And then if we connect those, we're going to find the area of that shape, which is a trapezoid. So the area, the exact area, which is indicated by the definite integral, can be approximated by finding the area of trapezoid number 1. So the formula for trapezoids are 1/2 times base 1, which is going to be f of 1, plus base 2, which is going to be f of 3, times the height, which is going to be 2. Typically, I'm going to rewrite this better. Typically, we write it, because of the formula up above, we'll write 1/2 height first. I'll show you why I kind of wrote it the other way in class. There's kind of a faster way I like to compute these. But so that's 1/2 the height of the trapezoid times the sum of the bases. Okay? And that'll get us the area of our first trapezoid. We add to that another trapezoid here of width 2. If we go up to 5. Oh, I wanted to mention on trapezoid 1, remember this height, because it hits the curve, this height, this length is f of 1 because it stops at the curve, right? That means if I plug 1 into the function, I get the y value, which represents that height because it stops at the curve. So this height is f of 3. So the next trapezoid will be 1/2. It still has a width of 2. And one of its bases has a length of f of 3, and the other one has a length of f of 5. So that's our second trapezoid. Plus, trapezoid 3 has the same width of 2, and it's got a height of f of 5 plus f of 7. And I connect the corners, and that'll be trapezoid 3. Notice that I do have the f of 1 and the f of 7 in the trapezoidal approximation. So this is what we would work out. Again, you can kind of pump that out on the calculator. Your approximation should come out to be about 38.6 repeating. And we've got an under approximation here because we've got all this underage. It's not that much actually, but there is underage there. All right, let's move on to the next one. We're going to do one more trapezoidal. This time the heights are going to be 1 unit. So maybe we don't have to, well, I guess I should draw them all out. So I'm going to pause the video. You should do the same. Draw these trapezoids out if you can, and try to start making your formula for your sum for your approximation. All right, so here's our picture. If you start building, hopefully you already did this, but the exact area can be calculated by the definite integral from 1 to 7 of f of x. But we're going to approximate that by doing the area of each trapezoid. Now, keep in mind that I can factor out the 1/2 times the 1, because that's going to be the width of these, and it's going to show up in every term. And then what's going to happen is for the bases of the trapezoid, the first one will have a length f of 1. That's this guy right there. Plus f of 2, plus another f of 2 for the next trapezoid. That's the basis for trapezoid number 1. These are the, These are the bases for trapezoid 2. And notice there's a repeat of f of 2. So what we can do is we can say that we're going to say there's two f of 2s. One for the base of the first trapezoid and one for the base of the next trapezoid. So then 2 times f of 3 for the same reason. Right? If you look back at one that we did out only 3 times, but you can see that f of 3 is counted twice. F of 5 is counted twice. F of 1 and f of 7, the first base and the final base, are only counted once. So you got to, again, muscle this out on the calculator up until I get to 2 times f of 6 plus 1 f of 7. There's only 1 on that last trapezoid. Whoops, I'll do that. You muscle that out, and you get 39.6 repeating, which rounds to that guy. And again, that's going to be an under approximation. So now, based on all these approximations, let's make a list here and keep track. I have them written down here on paper. So let's see. Our left-hand Riemann sum interval of 2 units. I'm just going to copy these down. All right, and these were under or over. So this one was an over approximation. This one we said was an over. This was an over. This one was an under. This one was an under. This one was an under. Then we had the midpoints kind of looked like slightly an over. And then the trapezoidals were slightly unders. Now, this list is interesting to look at. First, I want to just look at left-hand versus right-hand Riemann sums. The more rectangles we added, we said they were getting closer to the exact area. So this was our over approximation, and we kept adding more and more rectangles, and you can see our area getting closer and closer to the actual area. This is where limits are going to come in when we start talking about our shortcut. Right? There's a limit there for the area. In our under approximations, when we did the right Riemann sums in this case, they were under approximations. They're not always, by the way. Sometimes the left is the under and the right is the over and vice versa. But we are approaching our exact area from being too small. Sorry, I drew these the wrong way, so I should have flipped them. So this one's coming from under and approaching our exact area. So when we're too high, it looks like we're crunching down on a number less than 40.9. And then when we're coming up from the bottom with our under approximations, 38.9, you could say we'd have to do more and more rectangles, but maybe the exact area is 40. Maybe that's the number they're squeezing on. We can look at some of our other approximations, and they're a little bit closer. So it looks like our closest approximations here are these guys. And then this guy. And those get even closer. One's over, one's under. It looks like it's converging on 40. That would be my guess. The exact area is 40. But we're going to figure that out next lesson. And when we come back here, we'll do what we learned on this actual function and see what the exact area is. And see how good our guess is. Okay. Hang in there. We're almost done. This is our last page. So a lot of times on the AP test and some of the stuff I'll give you on assessment, we're going to have a table of values. So it's a little bit less work, but you really have to understand what you're doing here to figure out and approximate our areas given tables of values. All right, so let's look at this first one. We're going to approximate this. Now remember, this is the exact area from 0 to 25 using a midpoint sum and 3 subintervals. So they tell us the subintervals. So since there's 3 subintervals, our first interval can go from 0 to 7. Then our next interval can go from 7 to 15. And then our last interval can go from 15 to 25. All right, now they're saying use midpoint. So we know, first of all, this question's a little weird because 4 it's supposed to be the midpoint of the endpoints of our green interval. 4 is not the midpoint, but it's the information we have. It's close as possible to the midpoint. On the AP exam, I haven't seen one where it's like this. I mean, they would have made this an 8 so that 4 is exactly the midpoint, but we're just going to go with this. I know 4 is not the midpoint of 0 and 7, but it's the only information we have and it's close enough. So if we're going to approximate this area doing the midpoint one, we're going to say that from 0 to 25, f of x dx, that's the exact area, can be approximated by 7. That's the width of this first rectangle because we go from 0 to 7. And then the height, which is 6. So again, the thing here with midpoint is students will want to use the midpoint. We don't. Remember, it's the height of the midpoint that we have to use. All right, so the width is the width of the interval from 0 to 7. So that's 7. And then the height is going to be 6 plus. The next interval, our purple interval, has a midpoint of 12. Again, that's not the midpoint of 7 and 15, but the information we're given, that's the closest thing to the midpoint that we have. Sorry, I wanted to give us our midpoint in the middle here. So the width of this interval from 7 to 15 is 8 units long. And the height of the midpoint is -10. Remember, we're using the height of the midpoint, not the actual midpoint. And again, I'm using midpoint quite loosely here because it's not actually a midpoint. Then our last white interval, our midpoint is 20. In this case, it actually is the midpoint of 15 and 25. So our interval is 10 units long because from 15 to 25. And then the height of the midpoint of that interval is going to be 8. And that would be our approximation from this table using the midpoint rule, and that will get you 42. Now we're going to do a left-hand sum and 4 subintervals. So if we're going to use 4 subintervals, left-hand sum, the first interval will be 0 to 4. The next one would be 4 to 7. I don't know if these intervals are confusing, these brackets, but I'm going to go with them because I think they work out. So that's our second interval. And then our third interval would be from 7 to 12. Oh, I forgot to mention it goes from 0 to 15. So we're only going up to 15. And our fourth interval, did we use blue? We didn't use blue yet. Will be from 12 to 15. So now you have to really understand what's going on here. For using left-handed sums, we're going to start with our first integral. So from 0 to 15, the exact area d of x can be approximated by rectangles. The width of the first green rectangle is 4 because from 0 to 4 is 4 units long. And what's the height? Since we're doing left-handed sums, we're using the left interval of the left side of our green interval. Now with the purple, our length of our interval is 3, right? So that's the width of our rectangle. And then the height, since we're doing the left side of the purple interval, the height is now 6. Then for the white interval, the length of our white interval is going to be 5 units long. And we're doing a left-hand sum. So again, we're using the left side of that interval to get the height. So it's going to be 5 units long. And the height is going to be -5. And then lastly is our blue one. Our blue interval is 3 units long. And the height, we're using the left side of the blue interval, so our height is -10. Notice what I said before, that when we're doing a left-hand sum, we don't use the rightmost height. we do start with the leftmost height, so that's helpful as well. So when you calculate this estimate, we should get 23. Now we're going to approximate from 4 to 20. So the first thing we do is we get rid of those guys. And we're going to use a right-hand sum in 4 subintervals. So it looks like our first interval will be from 4 to 7. Then our next interval, I've been doing purple next, would go from 7 to 12. That's our second interval. Then our next interval would go from 12 to 15. That's our third interval. And then our fourth interval will go from 15 to 20. Now, in this one, we're doing our right-handed sums. So our first interval, so the integral from 4 to 20, that exact area can be approximated by these rectangles. The width or the length, the width of the first interval is going to be from 4 to 7. It's going to be 3 units wide. I think this got a little confusing looking afterwards, so I'm not going to draw it in there. But I'm using the green interval, so from 4 to 7, the width is 3. And since we're doing a right-hand sum, we go to the right-hand side of the green interval and we use its height. So since it's a right-hand sum, we throw out the leftmost height. And we're going to go all the way to the last one. So now the next interval, the purple one, has a width of from 7 to 12 is 5. And its height, since we're doing right-hand sums, is -10. Now we're doing the white interval. The next one goes from 12 to 15. So that's a length of 3. And its height is -2 because we're doing the right-hand side. I should have circled that height, sorry. And then lastly, the blue one from 15 to 20 has a width of 5. And then we're doing our right-hand sum, so the height of the right-hand side of the rectangle is 8. That approximation turns out to be -31. And lastly, we're going to approximate from 0 to 25, so we're using all of this. We're going to do the trapezoidal sum and 3 subintervals. So if we do 3 subintervals, that kind of means I got to look at this. I'm going to skip from here to here. That's going to be my first interval. And where that one ends, that's where the next one begins. Because if I did 0 to 4, then 4 to 7, I'd have more than 3 of them. So then the next one we've been doing is purple. So it's going to start where that one left off. And we're going to go to 15. And then the last one is white. We're going to start where we left off at 15 and go to 25. Those are going to be our intervals because there's 3 of them. So our first interval, if we're doing trapezoidal rule, 0 to 25 can be approximated by, we're going to go 1/2 times the width of that thing, 7, from 0 to 7. Then we have to do times the sum of the bases. So our bases here are 15 and -5. Right? Plus, since they're not uniform widths, I'm not going to factor out the 1/2. That was the other thing here. Notice our widths were different each time. So on these tables, I got to kind of just keep doing it. I can't factor it out because they're not of uniform width. On the purple one, we're going to go from 1/2, and the length of that interval is 8 from 7 to 15. So that's like the height of our trapezoid. And then base 1 of our trapezoid is -5. And then plus our other one is -2. And then lastly, the white trapezoid from 15 to 25 has a width of 10. And then times, we got -2 is one of my bases, plus 20 is the other base. That approximation, when you calculate it, works out to 97.